So in this video, I'm going to talk a little bit about the pinching theorem. It's a very important theorem in calculus. It allows us to say some great things about limits that we wouldn't normally be able to say if we didn't know otherwise. And so the idea is, suppose f, g, and h are functions with the property that near some value c. So this is my value c here. Around c, we have that f of x is larger than g of x, right? It's above g of x. And h of x is between them, right? So if I look at just this piece here, f of x is on top, g of x is on bottom, and then h of x is between them. And suppose that the limit as x goes to c of f of x equals the limit as x goes to c of g of x. So f and g are getting really, really close to each other. In fact, they're pretty much equal here. They have the same limit at x equals c. But remember that h was pinched in between them. H was between them around c. So the limit as x goes to c of h of x must have been between the limits of f of x and g of x. But if the limits of f of x and g of x are equal, we must have that the limit as x goes to c of h of x is equal to both of them, right? So our idea is h of x is being pinched between f of x and g of x. And so that allows us to say something about the limit as x goes to c of h of x that we may not have been able to otherwise. So as a result of this theorem, you may also see it as the pinching lemma, but I call it the pinching theorem. A result of this is that we get these two identities, these two limit identities. The limit as x goes to 0 of sine ax over bx is equal to a over b. And the limit as x goes to 0 of 1 minus cosine ax over bx is equal to 0. Okay, we're going to use these as identities to help us solve some limits involving trigonometric functions. Let's look at this first example here. I have sine 5 over 3x over 7 over 3x. Well, my identity says that the limit as x goes to 0 of sine of ax over bx equals a over b. So all I have to do is identify a and b, and this looks really similar, right? So my a is going to be 5/3 and my b is going to be 7/3. So this limit as x goes to 0 of sine of 5 over 3x over 7 over 3x is going to be equal to 5 over 3 divide 7 over 3, and we keep change flip, so I have 5 over 3 times 3 over 7, which gives me 5 over 7. Okay, and that's my limit. Very simple. Okay, and then, so the limit as x goes to 0 of tan 12x over x squared. Okay, so we're going to use the properties of limits here, namely the limit as x goes to c of f of x times g of x is equal to the limit as x goes to c of f of x times the limit as x goes to c of g of x. So we're going to use that here and break up this tangent, right? Because tangent of x is equal to sine x over cosine x. So I can rewrite this as the limit as x goes to 0 of sine of 12x over cosine of 12x over x squared. This is going to give me the limit as x goes to 0 of sine of 12x over x squared cosine 12x. Now I can break this up into the product, the limit as x goes to 0 of sine of 12x over x times 1 over x times 1 over cosine 12x. What I want you to notice is that this x squared was broken up into these two x's because x times x is x squared. And I just popped this cosine out too. So we know by our rule, right, we have that sine ax over bx is a over b. So this is going to be 12 over 1. The limit as x goes to 0 of 1 over x is actually infinity. And the limit as x goes to 0 of 1 over cosine 12x is going to be 1 over 1, which is 1. But this infinity will take everything out to infinity. So this limit actually does not exist. Okay? Moving on, I have the limit as x goes to 0 of 1 over x secant 7x tan 2x. So this is going to be the limit as x goes to 0 of, so recall that secant of 7x is the same as 1 over cosine of 7x. And then just like before, this is going to be sine of 2x over cosine of 2x, that tangent x. So I can rewrite this as 1 over x times 1 over cosine of 7x times sine of 2x over cosine of 2x. I can rewrite this now as limit as x goes to 0 of sine 2x over x times 1 over cosine 7x times 1 over cosine 7x. Sine, this is one of our identities, right? So it's the limit as x goes to 0 of sine ax over bx equals a over b. So my a is 2 and my b is 1, so this just gives me 2 over 1. The limit as x goes to 0 of cosine 7x is going to be 1, so I have 1 over 1, and then times 1 over 1. So overall, I'm just left with 2, and that is my final answer. Okay. Next, I have the limit as x goes to 0 of sine 5x cubed tan x over x to the 4th. So I can rewrite this as the limit as x goes to 0 of sine of 5x cubed. And then remember, tangent can be rewritten as sine x over cosine x over x to the 4th. So an important thing to note about our rule was limit x goes to 0, sine ax over bx equals a over b. It's important to note that the powers on x are the same. So in other words, these guys have to be the same. So another way that this might work is the limit as x goes to 0 of sine ax to the n for some positive n, we'll say positive whole n, bx to the n equals a over b. They have to have the same power. Okay, so in order to compute this, I need an x cubed in the denominator to take advantage of my identity there. So this will be I can rewrite this as the limit as x goes to 0 of sine of 5x cubed over x to the 3rd, times this sine x I can pop down here. I can have sine x over x from that remaining x from x to the 4th times 1 over cosine x. This is going to give me, using my identity that I have here, 5 times 1 times 1, which is just going to give me 1, right? Because this limit will be 1, and this limit will also be 1. Okay. Okay, and that wraps up my whole spiel on pinching theorem and trig limits. If you found this video helpful, please consider liking and subscribing. Thanks.